Genre: narrative nonfiction. Essential question: how can science help you find out how things work? Read how forces and motion affect our lives. A crash course in forces and motion with Max Axiom, super scientist. About Max: super capabilities, super intelligence, able to shrink to the size of an atom. Sunglasses give X-ray vision. Lab coat allows for travel through time and space. Origin: since birth, Max Axiom seemed destined for greatness. His mother, a marine biologist, taught her son about the mysteries of the sea. His father, a nuclear physicist and volunteer park ranger, schooled Max on the wonders of earth and sky. One day on a wilderness hike, a mega-charged lightning bolt struck Max with blinding fury. When he awoke, Max discovered a newfound energy and set out to learn as much about science as possible. He traveled the globe, earning degrees in every aspect of the field. Upon his return, he was ready to share his knowledge and new identity with the world. He had become Max Axiom, super scientist. By Emily. Forces that move us. Super scientist Max Axiom jumps right into the world of forces in motion at an amusement park. What a perfect day! And even though everything feels turned upside down, spinning, flying, jumping, and falling are just some of the amazing ways to move. But there's a lot of science behind the zoom around us. In fact, the world is full of all kinds of motion. Everything that moves needs a force to get it moving. Back for another jump already? You bet. A force is any push or pull on an object. Bungee jumping depends on a force called gravity. It pulls objects toward each other, and it keeps us on the earth. Gravity is the reason I fall down, not up or sideways. Phew! Moving can be thrilling, but I need a break. Snap! Snap! Hi, Rosita. What are you doing here? Hello, Max. I'm taking notes for the physics class I teach. Why are you just sitting there? Is something wrong? Once I sit, sometimes it's hard to get moving again. But once I get going, I often can't stop. That's inertia for you. An object at rest tends to stay at rest. An object in motion stays in motion. That's Newton's first law of motion. A still object needs a force to get it moving. Likewise, a moving object needs a force to change its direction, slow it down, or make it stop. For instance, inertia keeps that stroller rolling. Whee! Until another force comes along to stop it. Aww. To cure your inertia, you just need a little push. Come on, let's go ride the roller coaster. Let's move. Isaac Newton. Isaac Newton, 1643 to 1727, was the first person to realize that certain laws of nature explained all motion on Earth and in space. He also was the first to explain the idea of gravity. Stop and check. Reread. Why does a moving object need a force in order to change direction, slow down, or stop? Reread to check your understanding. Here we go. I feel like I'm being pushed to the back of my seat. That's inertia. When the ride starts, your body is at rest. When the chair moves forward, your body wants to stay at rest, but the chair moves into you. The chair's forward motion makes you feel like you're being pushed to the back of your seat. Wow, how does this roller coaster go so fast? The force of gravity is increasing our speed. Speed is how fast we are going at any given moment. Acceleration is how much speed we pick up as we go down the hill. Acceleration causes us to move more quickly at the bottom of the hill than we did at the top. That bar digging into my stomach must be inertia too. You got it. The ride comes to a stop, but your body wants to keep moving. The lap bar applies a force that keeps you from flying out of the car. So the lap bar stopped us from continuing forward on the roller coaster. What keeps that stone from staying in motion? Plop. Excellent question. You can't see it, but a force called friction stopped the stone. Friction happens when two surfaces rub against each other. On Earth, gravity and friction work together to slow things down and make them stop. Friction in space. In space, there is no friction. If you kicked a stone, it would keep going and going and going. That's why astronauts are tied to the space station when they do spacewalks. Otherwise, they just float away. Stop and check. Reread. How does friction stop a roller coaster? Reread pages 70 through 71 to explain how friction works. Brakes on the roller coaster used friction to slow us down too. Come on, I'll show you how. Each roller coaster car has two brake fins attached to its underside. As the cars approach the station, these fins slide between two sets of brake rails. I see. When the brake rails squeeze against the fins, friction stops the cars. I had a great time, Rosita, but I've got to run. My nephew is having his birthday party over at Skater's Paradise. See you later, Max. Motion is a weighty issue. Juggling these bowling balls is wearing me out. I don't know why that guy is so tired. Juggling is easy. The juggler on the right is tired because he's using more force to throw and catch heavier objects. He's showing us Newton's second law. The amount of acceleration that a force can produce depends on the mass of the object. What's mass, Uncle Max? Mass is the amount of matter in an object. The bowling ball has more matter in it than the tennis ball, so it feels heavier. Think about it. Which ball would be easier to juggle, Nick? Gravitational pull. Weight is different from mass. Weight is determined by gravity's pull on an object. Each planet in our solar system has a different gravitational pull. If you traveled to each of the places below, your mass would always be the same, but your weight would be different. Multiply your weight by the numbers shown below each planet to find out how much you would weigh there. If you weigh 100 pounds on Earth, you would weigh 38 pounds on Mars, and 236 pounds on Jupiter. Venus, 0.88. Mars, 0.38. Jupiter, 2.36. Saturn, 0.92. Neptune, 1.13. I have another way to think about Newton's second law. I need 2 volunteers. Pick me. I'll do it. I'm going to push both of them with the same amount of force on a level surface. Who do you think will accelerate faster? Johnny's bigger. He'll go faster. Jenny's an awesome skater. She'll win. Both of my arms are equally strong, so the amount of force will be the same. Let's see who gets a faster start. Like the tennis ball, Jenny has less mass than Johnny, so she gets a faster start with the same push. Johnny would need a stronger force to get moving as quickly. I'm like the tennis ball. Does that make me a bowling ball? Uncle Max, Jenny won the race on a flat surface, but I've noticed that the bigger kids always travel farther than the smaller kids when skating down a ramp. Sometimes having more mass can give you an advantage. Let's have Johnny and Jenny race again. In the last race, we wanted to see who would get a faster start. This race is for distance. I'm going to release you at the same time. We'll see who travels farther without pumping. Johnny's got it in the bag. No way! Jenny will beat him easily. Stop and check. Make predictions. Who will travel farther when released down the ramp? Use what you learned about forces in motion to make a prediction. Do you see that? Gravity pulls them down the ramp, but Johnny travels farther than Jenny. Max, what happened? I got a good start, but Johnny just passed right by me. Johnny's larger mass takes more force to slow down or stop than your smaller mass. Friction between your wheels and the ground was the main force, slowing both of you down. Johnny needed more friction to stop, so he traveled farther. Time for cake! I don't think these kids will let a little friction stand between them and chocolate cake.